Well then, we are now recording. So I will hand it off to the students here to finish out our last pipette presentation of the day.
Okay. Good afternoon, everybody. My name is Joshua Orteza. I am joined by my teammates Sam Mangoni, William Cow, and Hen Glass. We are Team Early Birds, and we are here to hopefully get a worm today. We will be presenting our automated pipette. Next slide, please. So we are set to speak on the overall objective, the initial design and its various flaws, our final design and fixes, a few analyses, and the outlook for the future. Our basic objective here is to take what you see on the left, which is a standard pipette, and automate the process. So our team was responsible for covering the 100 to 1000 microliter range, and we are required to be within a 5 microliter band of the desired dispensing value. Next slide.
Our initial design consisted of an EMA 17 stepper motor that would essentially just move a cylinder up and down over a plunger. The plunger has a through hole through it, and the cylinder is also hollow, so it would essentially just move a column of air that would pick up a substance and also eject the substance. One key feature of our initial design was that the motor was offset from the cylinder, and this allowed for two distinct advantages. One, we were able to reduce the overall height of the assembly, and two, we were able to prevent rotation. So as the lead screw rotated, we didn't see the cylinder also rotate. Next slide, please. There were a few flaws with our initial design. One, our housing was too wide. Our second flaw was that the tool plate was too low. So the tool plate is what attached the pipette to the XYZ. But our tool plate was at the bottom of our pipette, and all of our mass was also concentrated at the plate at the bottom of our pipette. So it essentially became an inverted pendulum, and it was really unstable. But the biggest flaw that we had was a bending moment. So because our lead screw was offset from our cylinder, we did see a bending moment. Next slide, please. And here's an illustration of the bending moment that we saw. So essentially, because of the bending moment, our cylinder was grinding against the plunger that was inside of our design, and it didn't allow the cylinder to actually translate up and down, which was a really big problem for us that we discovered during testing. Next slide. We tried to do a couple of fixes. So one, we tried moving the location of the lead screw, which you'll see in the left picture. So we just tried moving where that hole is and where that lead screw goes to the top piece. But unfortunately, we did still have a bending moment, and we weren't able to translate the cylinder up and down. So our quick fix during testing was we just punctured 2 holes through the side of the housing and string around our cylinder to pull our cylinder in the opposite direction of the bending moment, which again, it was just a quick fix. If we could play the video, please. But the cylinder or the string was effective in counteracting that moment, and we were able to move the cylinder up and down during testing. But this really paved the way for our final design, where we decided to make the lead screw in line with the cylinder. Next slide.
Okay, so now I will be talking about what our final design ended up being. So this is an overview of our final design, and we were able to fix a few major issues. So the first and biggest one was that we made the plunger in line with the motor, so we got rid of that bending moment. We also moved the tool plate higher, closer to the pipette center of gravity, so that our system was a lot more stable. We also improved the tip ejector, which I'll talk about later. And then overall, our design just ended up being a lot more sleek. It's a lot thinner and less boxy. So first I'll talk about the housing. So our housing is split into 2 components. We have our inner housing and our outer housing. Both are 3D printed, and how it works is that the inner housing slots into the outer housing. So on our inner housing, we have an integrated motor mount and limit switch attachment, which was a big improvement because on our initial design, those were both separate pieces. So we were able to integrate it all into one piece. And then on our outer housing, we had a large slot that was really helpful for viewing it during its movement and also for troubleshooting during testing, so we could see what was going on. And we also have mounts for our tool plate and how it attaches to the bioreactor. So for our air chamber, it's split into 3 components. We have the lead screw nut, which is what attaches to our motor and lead screw. And then we have our top cylinder. So the top cylinder has a hole in it, which allows the lead screw to go up and down in. And we also added a press fit dowel pin for alignment. So how it works is in the back of our inner housing, we have a slot that runs up and down, and the dowel pin runs up and down the slot. So this prevents any unwanted rotation during its movement. And then we also have, so the top cylinder screws into the bottom cylinder, and it is sealed with this O-ring, which prevents any leaking. So the bottom cylinder is what our plunger goes into, and it has a reamed through hole for the plunger since it has O-rings on it. And then the end of it also doubles as a tip ejector, which I will talk about in detail soon. So for our plunger assembly, it's made out of steel and it's split into 2 major pieces. We have our plunger and our plate. So the plunger is actually welded here to the plate, and then the plate attaches to the bottom of the housing here. The plunger itself has 2 O-rings to prevent leaking, and the tip connects to the bottom of the plunger here. So as for how our tip ejection works, as you can see in our plate, we have a cutout. So the cutout is for that end of the cylinder here. So how it works is that when we're simply sucking up and dispensing liquid, we are operating above the range where the pipette tip would sit. And then when we are ready to eject it, we push the cylinder all the way down past the tip to eject it. So initially we designed it so that the cylinder would simply just hug the pipette or hug the plunger and be able to knock off the tip. But we were having issues with consistency with that. So we added this 3D printed guide piece, which is slanted. So as the cylinder moves down, it's pushed forward into closer to the plunger, which allowed us to eject the tip 100% of the time. And then here's a quick video of it working.
Very good.
And that concludes the overview of our final design.
Here,
You're
I just
muted.
wanted to highlight a few customer requirements that are met in the design. Our assembly does take less than 5 minutes to assemble. We attribute this to the standardization of the fasteners. We use M3 fasteners primarily, except the 2 fasteners used to hold the limit switch in. Our design weighs about 2 pounds, with the heaviest pieces being the motor and the bottom plate. So there's room to expand and move away from the use of PETG if you're looking for something more sturdy. The max rotation of the assembly while still interfacing with the controller was found to be 3.96 degrees, and that was determined during testing using a dial indicator. Next slide.
Hi, I'll be tackling one of the critical customer requirements regarding the operational lifetime of at least 10 years and operating in a temperature range from 4 degrees Celsius to 70. So in regards to the lifetime of the motor, the NEMA 17 motor is expected to last at least 10 years with adequate function and maintenance, as long as there's occasional cleaning, and when you use the motor, it doesn't exceed the holding torque. In regards to the O-ring lifetime, the material is a Booner N rubber, which withstands a temperature range from -40 degrees Celsius to 121 degrees Celsius. And this is beneficial as it prevents thermal degradation and thermal extrusion, which is a failure mode of some O-rings. There are also no chemical failure modes because the material has high chemical resistivity. Some other failure modes are resolved with even surface finish with lubricant. There's low pressure suction, so high pressure failure is no problem. And there's the use of double O-rings for better seal. And careful installation is also advised to prevent installation damage. And most of our housing is made from PETG for the inner and outer housing. It has high chemical resistivity and it has low thermal coefficient of expansion. Upscaling, we could make it out of aluminum and it'll still have the same properties. Next slide. Here we can see some O-ring compression details about the plunger. So it's a double O-ring piston seal. What's unique about our design is it's a female to male end. So we have a double O-ring piston seal instead of a female gland. It's going to be a hydraulic situation where the recommended requirements is an average deformation of 10 to 15% and a compression by 1 to 3% of its circumference for a good seal. So for the compression squeeze, as you can see here, it is a 21.35%, which is perfect as you want a 20 to 30% compression squeeze for a good seal. And the compression set indicates the amount of permanent deformation of the O-rings. So you don't want a lot of permanent deformation of the O-rings as you need them to consistently have a good seal to last a 10-year lifetime. So as you can see here, it has a 13.16%, which is quite good. Next slide.
So now talking about fail-safes, we wanted to make sure that our design wouldn't have any sort of catastrophic failure modes. So the first thing that we tested was the structure of the heat inserts, the metal inserts that get set into our 3D printed housing. So to make sure that these wouldn't fail, we used Tresca's failure theory to determine the allowable force that we could see on each insert, and determined that the allowable force is higher than the force that we would see from the motor, proving that the heated inserts would not fail.
We also wanted to ensure that the weld that holds the plunger to the plate wouldn't fail. So as you can see in the top right, there's 2 fillet welds that currently hold the plunger to the plate. And you can see in the free body diagram on the left, we essentially modeled the force of the motor going down on the plunger, and then each fillet weld was assumed to hold an equal amount of that force. Next slide, please. So first, the shear stress was found with Tresca's failure theory. So basically just the yield stress of the steel filler material was found and divided by 2. Then the effective area of the weld was found just by multiplying the dimensions of the weld. So the height times the width of the weld times a factor 0.707, which is derived in Shigley's mechanical engineering book with the Bonomisi's failure criterion. The maximum force was found just by multiplying that shear stress by the effective area, and it was determined that the maximum force on the weld was about 600 pounds of force, which is much, much greater than the maximum force of the motor. Thus, we wouldn't see any kind of failure from the weld.
So overall, we determined that our failure mode definitely is not catastrophic, and what will happen is simply that the lead screw will bottom out and the system will stop moving.
Here I'll be addressing one of the critical customer requirements for our volume range of 100 to 1000 microliters with uncertainty of 5 microliters. So on the left-hand table, you can see the uncalibrated volume when we did our testing. And you can see that at in increments of 50 microliters, we tested for different volumes of liquid to find the disparity between what was specified and what actually was dispensed. And you can see the uncertainties start to compound linearly in the bottom right. And as a result, we made a calibration curve, which fit quite nicely. And using this calibration curve, we can edit our code so that we specify a different volume to hit our specified volume. And above, you can see the table for calibrated volume hitting all within our 5 microliters. And in specific, when we did some final testing with 200 microliters, we hit 201.4 microliters and 199.8 microliters, which is well within the 5 microliter range. Next slide.
So some additional requirements we'd like to highlight is that we've been able to integrate our design with the tool changer, as it is our primary means of interfacing with the rest of the bioreactor. The integration of stainless steel for our plunger design and in conjunction with the 6061 aluminum used for the cylinder ensures that the components that are interacting with lab materials are non-reactive. The integration of our limit switch creates a reference point for the cylinder so it knows the distance to move to displace the required volume that allows for automatic addition and subtraction. There is no cross-contamination between the individual wells due to the use of disposable pipette tips. And we also created a backstop with the lead screw and the aluminum cylinder to prevent any liquid entering the plunger. And during testing, we did not observe any aerosols or backsplash. Next slide. Looking down the line, there are three main aspects of the design we would like to improve. The clearance between our tip ejector and the plunger would sometimes result in the ejector failing to remove the pipette tip, hence the guide. This could be attributed to a plethora of things that could be tested in the future, such as mounting the motor in the housing a different way. It could be the deflection of the cylinder due to the dowel pin riding in the slot. And it could be a manufacturing defect, such as the O-ring grooves bowing out a little bit. We do want to redesign the weld for manufacturability. This requires a clever way of doing it, but we have discussed using external threads or maybe manufacturing in a way such that the plunger just snaps into that bottom plate. Lastly, a simple change that we want to do to improve the weight is to just reduce plate thickness. That will be dependent on how we choose to mount the plunger in the future. Next slide. That concludes our presentation, and we would like to open the floor to any questions.
All righty. Thank you, guys. Very well done, at least in my opinion. I had one comment on your data, but then I'm going to hand it off. But in case I don't have time, in case we run out of time, I want to let all of the panelists go first because they have another presentation at 4 to get to, and then I'll ask my question at the end if we still have time. So our panelists, our core sponsors, fire away.
Hey guys, this is Tom Singer, Northern Grumman. I'll say you did a very good job, and I like what you've got here. We've gotten through almost a whole day. There's only one more presentation. I haven't seen a single FEM, and I really appreciate that.
Tom, I told them I was going to fail them if they did a FEM.
Thank God. I really liked putting the whole system in line and getting rid of those bending moments. You saw that you had some problems with those. When things move and they're out of line, they rack and it causes issues. It causes, even if it's not an immediate issue, it causes long-term wear that doesn't necessarily need to be there. So I really like the concept of just that inline system. One thing I'll pick on in your calibration, and this isn't necessarily a problem with your design, but you're showing like 10 digits of precision on things, which is far more than necessary. So that's just one of those things that looks like, you just copy and paste from Excel without thinking about what your data really means. So from a cleanliness of presentation perspective, that would be nice. And I'll also add that the video of the ejector operating was nice, and I'd like to see more of that. I'd like to see kind of videos of how you anticipate your system operating. I liked it very early on. You kind of showed it as part of a larger system, which I don't think many other groups, if any other groups, have done. So I like getting that picture of it within the overall system, but kind of seeing how it operates within that system would be nice. So more of that.
Yeah, those are all really good comments. Thank you.
We also have a 2-minute video of us assembling it and showing it in action. If you need, we can.
Was that on the landing page? I might have missed that with like poster presentation stuff.
In my horrifically overworked state, I forgot to give them a deadline or an assignment to submit the 2-minute videos. So they're submitting their videos along with their final reports, and then we're gonna add all of their little 2-minute videos at the end of the semester. So that way there will be a redirection to it, and we'll get a link set out to all the core sponsors with those.
Yeah, that'd be great. I think that would give a real clear picture of how you anticipate your system operating. And just real quick, so you've got some 3D printed parts going on, right? And I'm wondering, how does that scale up to production?
So I can answer that question. So thankfully, most of our key components are already made of aluminum or steel, such as those that plate that Josh addressed before, and the 2 cylinders. So scaling up for manufacturing for the housing, that would be the main 3D printed components, and that could easily be manufactured. I added extra fillets to support the 3D printing, but those could easily be removed for faster and better mass produced. And the material could simply be aluminum because our weight is 2 pounds, which is far below the requirement. So we still have a lot of leeway to work with.
Cool, thank you.
Do we have additional questions, or do I get to ask now?
I don't have an additional question, but this is Rick Miles from Northrop Grumman. I do appreciate you showing your lessons learned. I think that's very useful just from an engineering perspective, right? Not to be afraid to show where you experienced failure and how you went about correcting it. I think that's a very, very, very useful.
Thank you. Yeah, for our initial design, it got to the point where we were so just lost on why it wasn't moving that when we removed the cylinder from the plunger, we actually observed tons of aluminum shavings from just the motor attempting to move it versus it actually moving.
I guess I'll go ahead and ask my question then. So I've actually got 2 of them. You mentioned back close to the beginning that you guys did testing on angular misalignment of the tool plate, which you're the only ones so far today, unless I don't remember correctly, to mention having done that. But you said it was 3.96 degrees, which is a lot. So what does that equate to for tip position down at the bottom relative to your tool plate? William, if you're talking, you're muted.
Okay, sorry, I have some. Okay, so I found that max rotation. So for the max rotation, that was for the tool plate, the tool holder by Noel, attaching to the XYZ XYZ system.
Right.
And I figured out the that max rotation from using a dial indicator to measure the deflection. So I measured the height from that axis from the where the it was connected. So that was about 6.5 degrees, 6.5 inches down. And I kept I had the motor continuously run every 2 seconds. And I would occasionally slightly tilt it. And then once the electrical connection stopped, that's when I knew it was the max rotation before it couldn't continue to operate. And I found that the deflection at the bottom was 0.45 inches. So in regards, because of that 3.96 degrees, it'd be 0.45 inches off.
But we don't expect to actually ever hit even close to that angle. That was just a check to see like what the maximum it could even go before the whole thing just stopped interfacing with the motor.
Okay. Okay, that makes a lot more sense to me now. So
Yeah.
I'm like, how are you going to pick up pipettes when you're half an inch off?
No, yeah.
Like you're literally a pipette diameter off, more than a pipette diameter off. You're going to pick up, 3 pipettes away. Okay, cool. Did you do repeatability testing also to see like, hey, if I take it off and put it back on, what's my positional tolerance?
Yes, we did that, and we also did repeated testing as well for the volume testing. We we did before we did 100 microliter increments, and we did it 10 times. So we had to do what was that, 1,000 tests, I think. No, wait, 110. 100, yeah, it was 100 tests, and we also did more tests after that. So there's a lot of averaging out, so we could have like a 95% certainty with that for 10 times.
Cool. All right, any last questions? Oh, all right, Dr. Traum is hopping off to go get the last MEC 2 presentation started. I'm going to, if I can find the link, pop it into the chat for everybody. So for the last MEC 2 presentation, here is the Zoom link for the final presentation for today's presentations. So if you want to go and see the heliostat number 3 presentation, that is what's coming up next.